Considering the pattern formed by the last three sections, you might have been able to guess without looking that this section would be on the volume of a pyramid and a cone. Before I get to those formulas though, I'm going to show you a demonstration about how the volume of a prism compares to the volume of a pyramid. Here I have one prism on the left and one pyramid on the right. You should notice that both of these have the same height. In addition, they also have the same size base. The pyramid fits exactly on top of the prism. They form one shape. So why is this important? Why do we care about a prism and a pyramid that share the same base and the same height? Well, the question we want to ask is, how many of these pyramids would fit inside of this prism? What's your guess? Think about it, and I will actually show you the answer here in a second. Here I've filled my pyramid up with water. That's the first one. What do you think now of your guess? Here's the second one. And here's the third one. It takes 3 of these pyramids to fit in one of those prisms. On the screen I have drawn a square prism and a square pyramid that have the same base and the same height, just like in the demonstration. What you need to take away from that demonstration and remember is that the prism has 3 times as much volume as the pyramid. Or if you think about it another way, that the pyramid has 1/3 as much volume as the prism. Hopefully seeing that demonstration with my document camera will help you remember that the pyramid only holds 1/3 as much as the prism. Hopefully that will help you remember this formula. This is the formula that we have for the volume of a prism. This is not the pyramid formula yet. This is the prism formula you should already know. Since we know that this is the volume of a prism, think back to the demonstration. How does the pyramid volume compare to the prism? That's why I made a point of highlighting it. Their pyramid holds exactly 1/3 as much as the prism. This means that our pyramid formula is exactly 1/3 of the prism formula. That's all you do. You just add in the 1/3 fraction. For a cone, we will be doing the same thing that we have done the last 3 sections. If you want, you can use the same formula for a cone as you did for a pyramid. That works perfectly well. However, we know that for a cone, the base is a circle, the area of a circle is pi r squared, so we can substitute that in to get a cone-specific volume formula. If you want to memorize that cone-specific formula, go right ahead. But the 1/3 VH will work fine too. Now we come to Cavalieri's principle. In the book, this actually comes in section 11.4, but I put it off until now simply because this video was going to be so short otherwise. Let's say I have a stack of papers. Now let's say I take that same stack of papers and knock it over slightly. I have changed a right prism into an oblique prism. The height of my prism didn't change. The stack is still the same amount of papers, and they didn't suddenly get smaller. Pushing the stack into a slant did not change how many papers were in that stack. The volume stayed the same. Make sense? The same amount of paper is still in each stack. Cavalieri's principle is a very mathy way of saying that same concept. The actual theorem and what it says are not that crucial. What we want to take away from Cavalieri's principle is this. It essentially means that my demonstration with my stack of papers on the last slide actually worked. But that isn't the crucial bit. What was I trying to show with my stack of papers? I said my volume didn't change, even though I made my stack of papers switch from a right to an oblique prism. So the thing you really want to take away from this is that the volume formulas work on oblique shapes too. This is not true of the area formulas. The lateral area and surface area formulas do need right shapes and regular pyramids. The lateral area and surface area formulas absolutely do not work on oblique shapes. But the volume formulas do work on oblique shapes. That's what we take away from Cavalieri's principle.